And it's a great pleasure to introduce this year's speaker, Associate Professor Tara Murphy from here at the University of Sydney. She's an astrophysicist working here as well as being an ARC Future Fellow. She received her PhD from the University of Edinburgh, and her research today focuses on detecting and studying transient and highly variable objects in the sky. She also is very interested in data and using next generation telescopes, radio telescopes in particular. And much of her research is developing techniques for dealing with large volumes of data, what we call data-intensive research. She leads an international team of researchers searching for variable and transient sources with the Murchison Wide Field Array, as well as the Australian SKA, or Square Kilometre Array Pathfinder telescopes in Western Australia. Tara is also passionate about teaching and high school outreach. In 2014, she co-founded a startup company called Grok Learning to get high school students around the world excited about computational thinking. She has recently launched a MOOC on data-driven astronomy on Coursera. Tara played a major role in follow-up observations from the epoch-making discovery of gravitational waves from two colliding neutron stars, a very, very recent result which we're going to hear more about tonight. I'd like to now welcome Tara to give her Allison Levick Memorial Lecture entitled Breakthrough, the Detection of Gravitational Waves from a Neutron Star Merger. Let's welcome Tara.
Thanks, Warwick. I'm really honoured to be giving the 2017 Allison Levick Memorial Lecture, and I'm really excited to be talking about something that this is the first time I've ever given a public talk about something that's so recent, something that actually just happened a couple of months ago, and I'm excited to be able to share this with you. This is basically an unprecedented effort in astronomy. You might have heard, if you've been following in the news, thousands of astronomers around the world working together to understand what was going on in this very first time that we've ever detected gravitational waves and electromagnetic radiation from the same event in distant space. So I'm just going to start with a short video that we made about this, and then I'm going to unpack it. What do all these things mean? What are neutron stars? What are neutron star mergers? What are gravitational waves? And why should you care about any of this, other than the fact that it's really cool? So I'll start with a little video. I apologize, I'm in the video, and this time when I play it, I'll try not to interrupt myself when I'm talking. That happened last time.
We got the alert that a neutron star merger had happened at about midnight Sydney time.
As soon as I got notified about the event, I jumped in the car, drove to CSIRO, and we started observing straight away.
This is the first time that we detected a gravitational wave event that also produced light and radio waves from the moment when two neutron stars merge. Straight away, we asked for time on the CSIRO's compact array. The scheduled observers were kicked off, and we observed as soon as the source rose over Australia. Gravitational waves indicated that this was from two neutron stars merging. A neutron star is a star with about the mass of the sun, but squashed into a region about 10 or 20 kilometers across.
We targeted a series of galaxies that we thought might host the gravitational wave event, but then we received news that there was an optical event in the galaxy NGC 4993. And so we started targeting that galaxy over a series of days.
We spent a whole day looking and hoping to find a detection, and it wasn't until about a day later that we eventually made a detection. We all felt very, very excited and also quite relieved to have finally made it after weeks of work.
Follow-up to the gravitational wave event was an international project, and so there were observations, radio observations, carried out in the US using the Very Large Array. We collaborated with a group and were able to confirm our own detection with their detection of the source.
The galaxy this merger occurred in is 130 million light years away. And that means that when it occurred, dinosaurs were still roaming the Earth, and Australia and New Zealand were still joined together. We're still monitoring the radio waves because we expect this source to keep getting brighter. How bright the radio emission gets and when it peaks allows us to work out what's going on in the merger. It tells us which of our models is correct. Gravitational waves gives us a completely new window on the universe. We need radio telescopes and optical telescopes to help complete the picture. Australia has amazing telescopes and will be making major contributions in this whole new era of astronomy.
Okay, so that's a 3-minute summary of this talk. So what I want to do now is start from the beginning of this story. August 17 was about just before midnight in Australia. I was at a conference in the US with one of my colleagues who actually works on this same project with me, and we got a notification of the initial detection. So what had actually been detected? This is a video that shows you the famous chirp that LIGO detected. So we'll just listen to that. And then, okay, so now it's important here not to get confused. This event is not actually emitting these sound waves. What this is doing is converting the gravitational waves to something audible, just like the way your radio converts electromagnetic radiation to sound that you hear. Okay, so this is pretty cool. This is the first time this has ever been heard in human history, so I think we should play it again. And what you're listening to is the final 1,000 orbits of these neutron stars before they collide. And then what you're hearing, that ping, which is completely fake, that's just put in there so that you can tell where it's occurring, is 1.7 seconds later, you're seeing gamma rays, electromagnetic radiation, detected by the Fermi Gamma Ray Telescope. So this is the first time it's ever happened. Now, what did this look like to us in our conference? We were sitting there, and of course, the speaker was talking, and we were checking email. Probably shouldn't admit that. And what came through is something like this. So this is the actual GCN. So this is a circular that you receive via email, sent out to a private list of just about 3,000 astronomers around the world who had signed up to be part of this LIGO follow-up program. And so you can see they're very factual. There's no sort of chit-chat in these circulars. Gets straight to the point and tells you that LIGO has detected something that is consistent with a neutron star binary. Now, straight away, looked across the room at my colleague, and we couldn't talk because obviously there was a speaker giving their conference talk, but we were on Slack straight away, messaging each other saying, this is it. This is what astronomers had been waiting for years. Why? Because all of the previous detections that LIGO had made were black hole mergers. And black holes don't have any matter around them. So when they merge, they emit gravitational waves that are detected by LIGO. They cause gravitational waves, sorry, that are detected by LIGO. But they don't emit regular electromagnetic radiation. So although astronomers followed them up with our normal telescopes, we didn't actually expect to detect something. When we saw this circular, there was immediate excitement in the room. About half the people in the room were actually in the collaboration and half weren't. And there was chatter started straight away. People started ducking out, talking to their colleagues. In our case, we were thinking, when can we first get our radio telescopes in Australia observing this? It was the middle of the night in Australia. We knew that this region rose at about 11 a.m. the next day, and so we were straight away planning our observations and waiting to see when would be a good time to ring the director of the telescope and ask for time. My colleague was pacing up and down saying, ring them now, ring them now. I was like, it's 4 a.m. in Australia, and the source doesn't rise till 11, so let's wait a bit. So we held off until 6 before we called them. So this was the start of the story. Now, why was it important? Why did all these hundreds of teams around the world suddenly want to point their optical and radio and X-ray telescopes at this region? The first problem is that LIGO is an incredible instrument. It might be one of the most sensitive scientific instruments that's ever been developed, but it still has some weaknesses, and one of the weaknesses is it's very poor at triangulating where the event is coming from. So those previous binary black hole mergers you heard about, we knew they happened, but we only knew where, to a region of a few hundred times the size of the full moon on the sky. So it's like saying something definitely merged over there somewhere in space, okay? And so we didn't actually know exactly where. So the first job of the other telescopes is to pinpoint exactly where it happened. Now, this green region was the region we were looking at, And a few people compiled lists of the galaxies we knew that were in that region, and there was about 50 to 100 galaxies. So straight away, people started looking, scanning each of those galaxies and looking for something unusual. What were they looking for? They were basically just looking for a blast of radiation, so a new source appearing in one of the images. We had no idea when it would occur or if it would occur, and so we were just looking through all of those galaxies to try and find something. And that effort started straight away, within minutes of receiving this trigger. Now, how does scientific discovery work in this age? One of the things I want to talk about in this talk is how science happens. Science is often told of a story of sort of discoveries by lone geniuses. That's certainly not true in modern science. These are big projects, thousands of people involved, and of course the internet plays a critical part in every single bit. So this is the message. I mentioned Slack. For those of you that don't know, it's just a sort of instant messaging platform that a lot of people use to collaborate, work on. This is the Slack messages between two of the team members that made the first detection of electromagnetic radiation from this event. And what they were looking for is something called a transient. And transient just means what it does in English, something that appears or disappears on a short time scale. So they were looking at images of the galaxies in this region, and then one of them says, found something. And that was the start of the next few months of work for the astronomy community. So this was about 11 hours after the event, and it was actually about an hour into our own observing program with our radio telescopes in Australia. We started off scanning all the galaxies as well, about 50. When we got the alert that someone had discovered an optical source, so with visible light, we immediately thought, well, hang on, it might be a red herring, so let's not completely divert from our strategy. Let's keep looking at all 50, but let's pay extra attention to that galaxy. Now, what was that galaxy? Here is a Hubble Space Telescope image of that galaxy, and it shows exactly what I mean by a new source appearing. So what you see in the center of this image is a large collection of stars that make up an elliptical galaxy called NGC 4993. And what's in the little box is the new source that appeared. So literally, astronomers look at previous images of that galaxy, and then they look at the new images, and they say, something has happened. Now, this happens all the time, actually. This is how we detect supernova, for example, when they go off. So this is a pretty standard thing to do, but in this case, it was pretty exciting because no one had directly observed a neutron star merger like this before, and nobody had detected any electromagnetic radiation from a gravitational wave event. So people immediately were getting extremely excited about this discovery. So that was the start of the electromagnetic follow-up program. And I'm going to tell our part of the story a bit later in this talk. But what I want to do now is go back to the beginning a little bit and unpack some of this jargon that I've been saying. What are gravitational waves? What are neutron star mergers? And put that into context so that we know why this is so exciting. So let's start with the first question. What is a neutron star merger? And actually, before we answer that question, we should probably ask the question, what is a neutron star? So this is a neutron star that's been conveniently hung just above a city. You wouldn't normally do this because it would be not good for the people living in the city. But for the purposes of this explanation, what we're seeing here is what a neutron star might look like. Now, a neutron star is basically the dead remnant of a star that has exploded in a supernova, and what's left behind is this incredibly dense material consisting of a very high density of neutrons. It's like taking the mass of the sun and squashing it into a region about the size of Sydney, which is why that neutron star has been hung above a city, to make that point. So you've basically got something the mass of our sun, but squashed into the size of a city. It's the most dense material we can imagine. It's the most dense thing except for a black hole itself, which, as we know, no light can escape from. So it's kind of the most dense, normal astronomical object that we could observe. And this is the first player in this story of a neutron star merger. So what happens if two of these neutron stars with this incredibly dense neutron-rich material get too close to each other? So what happens when two neutron stars collide? Okay, so what we're seeing there is two neutron stars that have got locked into an orbit, and this can happen anywhere in a galaxy. Stars can get close enough that they start orbiting each other, and because of just regular gravity, they can't escape from that orbit, and they get closer and closer together until eventually they merge. And remember that sound, the chirp that I that played at the beginning, is the final 1,000 orbits before that merger happens. But when they merge, and I'll just play that again with the sound a bit down. Okay, when they merge, it doesn't just form some new massive object, and I'm not going to say what that is at the moment, but also because neutron stars have all this matter, then what happens is an enormous blast of radiation. Firstly, gamma rays that go out in a really narrow jet, and that's what was detected by the Fermi telescope. And then a cocoon of material from the rest of the matter blasts out into space, and that was the thing that was detected by the optical telescope, so visible light. After that, the shock from that propagates through the interstellar medium, so the region around the stars, and the shock the shock that causes is what we ultimately detected in the radio. So this is a really complex event. It happens over a period of time. We detected the radio emission several weeks after the initial event. The visible light was detected about 11 hours after the original event, and the gamma rays were detected 1.7 seconds after the gravitational waves, and we'll talk about that in a minute. So we've had a suspicion for a while that we've been observing neutron star mergers, and that's because we've been observing these things called short gamma ray bursts. But even though neutron star mergers were the best theory for what was going on with short gamma ray bursts, like the thing Fermi detected, we didn't actually have conclusive proof. And this event is the first time we've been able to connect together that bit of that astronomy puzzle. Now, this is one of the reasons we're excited about this is one of the most energetic things that can actually happen in the universe. And we often say things like that. Astronomers and physicists, we often say massive because we mean has lots of mass, which translates to sort of like it's really heavy, but I can't say that as a physicist because that's not quite right. We also say, but that's sort of what it means, but we also say really energetic, and that means generates lots of energy. What does that really mean? How much energy do these events create? And let's have a look. So how energetic are neutron star mergers? So I actually want you to answer this question, but firstly I'm going to give you some information that you need to answer it. So we measure energy in joules. That's the unit that physicists use to measure energy. And 1 joule is like the energy required to heat a gram of air by 1 degree Celsius. So some of you that do physics and science will be familiar with joules. For some of you, it's a new concept. But basically, this is the way that we measure how much energy something has. Now, without giving you any more information, does someone want to take a guess at how much energy neutron star merger creates? 10 to the power of a few hundred. That's actually the only time anyone's guessed something that's too far. So less than that. Yes. That's actually a pretty good guess, and I know that you're a physics student, so that's probably why it's a good guess. But it's not. You wouldn't actually pass the exam with that, unfortunately. Not good enough. No. So let me give you a few more numbers. So we've had a guess on both sides. So let's think about some things we're kind of familiar with on Earth. There's a lot of analogies to explosions in this, but the energy released by an explosion of 1 gram of TNT gets you into the kilojoule regime. And interestingly, that's also similar to the energy in a AA battery. So that's something that you can get a grasp on in terms of how much energy we're talking about. Now, if we go to a larger amount of TNT, a kilo, then we're into the megajoules regime. And so we're starting to talk about a pretty significant amount of energy. But then it gets really interesting. So if you think about the energy in the jet fuel of a Boeing 747 at maximum capacity, you're in the terajoules regime. And then you get, unfortunately, into comparisons with nuclear bombs. So for example, the largest nuclear test ever conducted on Earth is a 50 megaton bomb, and that gets you into the petajoules regime. Then you can go, to go any further than that, you have to go beyond individual things and into things like the total amount of energy. For example, the yearly electricity consumption of the whole world in 2008 gets you into the exajoules regime. And this is 10 to the 19 here, which is close to the guess from up the back, and is nowhere near the amount of energy that's generated by a neutron star merger. So that's our first page. If you'd known there was 2 pages of numbers, you might have made a bigger guess. So then we get into zettajoules, and pretty much the largest amount of energy that would be associated with anything human, which is, say, the amount of energy estimated to be in the world's coal reserves, and that's in the zettajoules regime. And then you're well and truly into things that are only astronomical. So, for example, the energy released by a typical solar flare, yottajoules, and even the total energy output of the sun every year, 10 to the 34 joules. This is, I think, the biggest thing we can really imagine in terms of energy that's associated with the Earth in some way, because that's the total energy output of our closest star. But it's still nowhere near as much energy as produced by a neutron star merger. And I think we've run out of prefixes as well. I personally have never used anything bigger than yottajoules. I might be wrong. So what are we talking about? The total energy of a merger emitted in electromagnetic radiation is 10 to the 43 joules. And if you look at how much emitted in gravitational waves, 10 to the 45 joules. The only thing bigger than this in the universe that we can directly observe like that in a single event is a different type of gamma ray burst. So we are truly talking about some of the most energetic things that ever happen in the universe, which is pretty incredible. And what that partly means is that we can do physics, we can study physics in that context that we just can't study on Earth. Of course, you can't set up a lab experiment that allows you to generate 10 to the 45 joules of energy. And we already discussed the unfortunate nature of the largest energetic things that are human created, which is basically nuclear bombs, and they're not even in the same league. So these are hugely energetic events, and therefore a great place to look at extreme physics that we can't really study in any other way. So, neutron star mergers, very energetic is the summary. But next, what are gravitational waves? So I've sort of talked about the astronomy there. What are these things that we keep talking about, gravitational waves, and what do they tell us? Why is the whole world so excited about them? Why did they win the Nobel Prize earlier this year? So here's a little animation. Gravitational waves are ripples in space-time that are caused when you have something massive, in other words, an object that has lots of mass, accelerating. And so one of the situations that occurs in is where you have these 2 neutron stars that are orbiting each other and being drawn together by gravity. Now, gravitational waves are extremely, so they've been predicted for a long time, obviously by Einstein, and I'll talk about that in a minute. They have actually been observed indirectly before, so, and that actually won a previous Nobel Prize. So there was a binary neutron star system that was observed to be, the orbits were slightly slowing down. And the rate at which they were slowing down matched exactly the predictions from the general theory of relativity that Einstein predicted. So we knew indirectly, and like I said, that won previously a Nobel Prize, we knew indirectly that gravitational waves seemed to be a good model for what we were observing in the universe. But what we had not done is made a direct detection. And as an observational scientist, which most of my colleagues are, you really want to see something, measure something, to confirm the theory that's put out there. So one of the reasons that we're so excited is this is the first time they've been directly detected. Now, how does that detection actually happen? This is pretty incredible. And actually, so most people that know me know that I'm not a lab person, and I don't, lab was not my best subject at uni. This LIGO detector is actually really similar conceptually to an experiment we had in the second-year lab called the Michelson interferometer. I could never get that to work, not even once did I ever do an experiment with that worked. But in principle, interferometers are really cool. And when you build them at this level, so this is something that has been worked on for decades, to create an instrument that conceptually is extremely simple, but has the most incredible precision that you can measure a ripple in the Earth that changes the distance of something by 1,000th of the size of a proton measured over 4 kilometers. It is insane. And I don't, even as a physicist, don't really hardly believe it works, particularly not after my undergraduate lab experience where it just literally didn't work. So here's a little video about how the LIGO instrument detects gravitational waves on Earth.
To measure this stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves. And the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
So the concept behind this is extremely simple, but the precision engineering involved in actually creating an instrument that could do this is something that's taken a team of thousands of people decades to achieve. One of the things that's really interesting is it's also a great example of how you need in science reproducibility, because the number of different levels of noise that you have to remove from this experiment caused by everything. Imagine other things, anything else that's moving that could create things that might appear like a signal in this experiment. And one of the only ways you can ultimately confirm that it's a gravitational wave is by having multiple detectors. So there's one of these interferometers on one side of the US, another on the other side, and now one in Italy as well. And because you know exactly when they should detect that signal in relation to each other, if they all detect the signal at the same time, that gives you a lot of confidence that the signal you're detecting is real. So once the signal's been detected and an alert is sent out to the community, the astronomy community was sort of waiting to follow this up with their telescopes, and that's the story we've been talking about today. But why is that combination of gravitational waves and regular electromagnetic observing important? We're really used to observing the universe through all different wavelengths, and each wavelength gives us different information. We have gamma rays, we have X-rays, through to visible light and radio waves, and we understand how those observations work really well. Gravitational waves are a completely new window on the universe, and I know that that's said a lot, but in this case, it really isn't a cliche. This is a way of observing the universe we have never had access to before, and as a result, we can learn some interesting new things. So the first one is, you might have heard, if you've seen any of the news coverage, we proved Einstein right again. What does that mean? So, and actually, although this animation is from LIGO, it's a little bit deceptive, so I don't really like it. But the point that it's trying to make is that the first thing this demonstrates is that gravitational waves and electromagnetic radiation travel at the same speed. So, think about this. This galaxy that this merger occurred in is 130 million light years away. So that means that both of those signals have been traveling 130 million years to get to us. And yet in that time, they arrived only 1.7 seconds apart. So that means that they are traveling at the same speed to 1 part in 10 to the 15, or a million billion, or a quadrillion. I don't often get to say that number. So they agree to, with incredible precision. Now, some people will still be concerned about that 1.7 seconds, and it's true. It's not perfect. They're not exactly the same speed. Is that what it means? So remember I said this is a complex event. And my mic's falling over. Okay, remember I said this is a complex event. So the possible theories as to why there's a 1.7 second delay between gravitational waves and gamma rays being detected, there's a few possible theories. The first one is that they didn't actually come from exactly the same place. So in other words, the gamma radiation comes a little bit further out, just as the jet is starting to come out of whatever is formed, and we'll talk about that in a minute. And so you're getting a very slight difference in the location of the event and the time of the event, and so they were not emitted at exactly the same time. The second possibility is that we know that the speed of light in a vacuum is constant, but we know that light, when it's traveling through a different medium, a more dense medium, is slower. And so if that gamma radiation is traveling out through a lot of material, dense material around the merger, then it could be slowed down slightly initially. So basically, there's lots of good reasons, astronomical and physics reasons, why there's a 1.7 second delay. But even given that delay, it still means that gravitational waves and light travel at the same speed to 1 part in 10 to the 15, which is pretty incredible confirmation. So the next thing that it tells us is something about the physics of neutron star mergers. I kind of already said this before, but why do we care about this? Because these extreme events are basically laboratories where we can do physics that we can't easily do on Earth. So this is a simulation of what might be happening in the very first few seconds after the merger. So when we talk about theoretical predictions these days, we're not just talking about some analytic equations that give you a few sort of basic predictions. We're talking about really complex computational models that are built on those equations, and they give you observational predictions of what you might see. We then use the observations at all those different wavelengths to pin down these models. And so even observations like our radio ones that are taken 2 weeks later actually help us determine what's happening in the first few seconds after this collision. Now, the next thing it tells us is something about how black holes form. So what actually happens? I've avoided saying it so far, I hope I have. What happens when these two neutron stars merge? Sorry, my mic is falling again. What's the output? So who would like to take a guess? What is created when two neutron stars merge? You can just yell out.
A neutron star?
A bigger neutron star. That is a very good guess, and that is one of the possibilities.
Black hole?
A black hole. That is another good guess, and that's the other main possibility. All right. And there's one more option, which you... Sorry.
That doesn't work.
It's just fallen. Okay. There's one more guess that's a bit harder, and that's actually that a supermassive neutron star is formed in an instantaneous moment and then collapses to a black hole. So we've basically got three possibilities. Either two neutron stars form a bigger neutron star, two neutron stars form a black hole, or two neutron stars form a bigger neutron star that instantly becomes a black hole. So they're pretty related ideas. Now, you would think we'd be able to answer that question pretty easily, but there's like 100 theory papers come out on this just since this happened, and we still don't completely know the answer. Because where this falls in terms of what we know already is pretty interesting. So the blue dots at the top, and I apologize, this is a bit hard to read because of these spotlights. The blue dots at the top are the known black hole mergers that LIGO has detected. So two blue dots. Sorry, we're just going to plunge into darkness. All right, so this is hopefully now better to see. So if you have two black holes that LIGO's already detected a few of these systems, and they form a larger black hole. And that larger black hole is almost the sum of the mass of the two originating black holes. They lose a bit of energy, as we've discussed. And of course, because of E equals mc squared, losing a bit of energy is the same as losing a bit of mass. And so the resulting black hole is not quite as big as the sum of the parts. Now, so there are known black holes at the top in blue, and in purple, they're black hole binaries that we've observed independently of LIGO. Now, at the bottom of this plot, so the mass is on the y-axis, at the bottom of this plot are known neutron stars. And right in the middle of the plot is our two neutron stars that were involved in this merger and the resulting thing, we'll call it. Now, that thing is more massive than the known neutron stars, but less massive than the known black holes. So conveniently falls right in the gap between them. And so there's actually some ambiguity about what's been formed here, whether we formed a neutron star or whether we formed a black hole. In this particular case, obviously, ongoing observations and analysis of the existing observations and modeling will hopefully determine the answer here. But in general, what studying these neutron star mergers will allow us to do is work out how, in more detail, black holes might form in the universe, and under what circumstances black holes would form as opposed to neutron stars. So this is another really interesting thing we can probe with these mergers. Now, the final thing that's really exciting, and you might have heard about in the news, is, wow, we produce gold. So when you Google where does gold come from, most of the results are something to do with digging it out of the ground. And that is certainly true. Gold on Earth does come from in the ground. But how does that gold actually form? Where does that gold originally come from? Well, we've known for some time, and I've put up a periodic table. Some people, like, this makes them so excited because they've still got a periodic table on their bedroom wall. Other people, like, this brings back trauma of high school and having to learn the periodic table. So I apologize if you're in that second category. This is a table that shows all the elements, and in this case, it's been color-coded as to where we believe those elements are produced. So hydrogen, helium, and a little bit of lithium are produced in the Big Bang. Most of the heavier elements, up to iron, are created in stars, okay? And then most of you will have heard the expression that the rest of the heavy things are from supernova. But one of the problems with that theory is that supernova can't explain the amount of gold and platinum that we see in our own galaxy. So we certainly know how gold is formed. It's in a process called nucleosynthesis. If you're a physics student and you want to look it up, it's our process, nucleosynthesis, specifically, that we're talking about here. But what we haven't been sure of is where is the site of this nucleosynthesis occurring, where the conditions are right. And supernova just do not produce enough of these heavy elements. So why are neutron star mergers a good candidate for this? Basically, to have our process nucleosynthesis occur, you need to have some kind of seed atoms like iron. you need to bombard them with a lot of neutrons, and you need an extremely high energy environment for that process to continue through to the production of things like gold and platinum. That's exactly the conditions that we have in a neutron-star merger. And in fact, in this neutron-star merger, some of the observations in infrared and optical were able to show that there was actually direct evidence that these elements were being formed. So that is, now neutron-star mergers are not as common as supernova, but they produce a lot more gold. So in this case, and I just wrote the number down so I don't forget, so in this particular merger, there were 10,000 Earth masses of heavy elements formed. So 10,000 times the mass of the Earth of these heavy elements were formed in this one merger alone. So there's some of the reasons why we care about neutron-star mergers. We are able to confirm predictions of relativity. We're able to study areas of extreme physics and how black holes form. And we're able to explain things much more relevant for us on Earth, like where our heavy elements come from. What I haven't talked about yet is how our story fits into this bigger picture. So where does radio come in? I haven't hardly mentioned that at all. I'll turn the lights slightly up again, hopefully, and tell you a bit about radio astronomy and our part of this story. So let's go back to the beginning of the story. And I said that we had got a trigger for about a gravitational wave event that involved two neutron stars. We had had 11 hours later an optical detection of something pretty exciting happening in this galaxy, NGC 4993. And that was all part of this worldwide effort of about 100 teams around the world searching for counterparts to this gravitational wave event. Now, this video is just showing in actual real time after the event, as night and day pass around the world, which telescopes in our collaboration, there's other collaborations also observing, were doing their observations. And you see in Australia, there are some telescopes, and these lights are terrible. I really apologize for the lights. I'm going to turn them off again because you can't see Australia, or I can't anyway. Oh yeah, there it is. Okay, so you see that in Australia, there are some telescopes on the east coast observing, such as SkyMapper and the Australia Telescope Compact Array, and there are some telescopes on the west coast observing, such as the Murchison Wide Field Array, ASCAP, and the ZADCO telescope. So they were the telescopes that we were using, and as you can see, there are lots of other telescopes around the world. One of the reasons that's important is because of this night and day thing that's happening. Optical telescopes that observe visible light, they can only observe at night. So when they can't observe anymore, or if the source sets in their time zone, they can't keep observing, but their colleagues around the world in a different time zone can keep observing the same thing. And so we sort of work as a team, observing around the clock around the world, and then combining our information together via sending out those alerts. So I mentioned a few times the idea that we're using different wavelengths. And again, this is my other sort of plot from high school that you might remember. When we do astronomy, when you go out and look at the night sky, it's beautiful to see that visible light. And incredible when you can go out somewhere away from the city and see our Milky Way. But we also use a lot of other wavelengths that aren't actually visible to our own eyes. So when you think about the Earth's atmosphere, it protects us from most of this radiation. So the Earth's atmosphere doesn't really let through gamma rays. It doesn't really let through X-rays, which is actually good, because if it did, we'd be fried. If you've been to a hospital, you know that you're not meant to hang around the X-ray machine, and the people that work on them have to wear shielding because they're really dangerous and they do actually fry you. So that kind of radiation, we couldn't have really evolved in the way we have if that was not being blocked by the Earth's atmosphere. What the Earth's atmosphere mainly lets through is visible light, and obviously we've evolved to have eyes that can detect that. And so an optical telescope, in a sense, is like an incredible version of your own eyes. And then the other main waveband that our atmosphere lets through is radio waves, and that's what I study. So radio waves are at the really long wavelength, low energy end of the spectrum. So you're talking about wavelengths of centimeters to meters long, the wavelengths of light. It's sort of a bit confusing. We sometimes say light to just mean all electromagnetic radiation. So the telescopes that I work on don't actually look like what you might think of as telescopes if you think of optical telescopes. So this is the Murchison Wide Field Array in Western Australia. It's a few hundred kilometres northeast of Geraldton. And it consists of a series of these antennas spread over several kilometres in the desert. This observes wavelengths of light around 80 to 300 megahertz. So that's the same kind of frequency as a lot of radio stations broadcast. So we are literally picking up the same kind of radio waves that your radio or TV use to send out their broadcast to you. And that's actually a problem for reasons that I'll explain in a second. So actually located right next to the MWA is another telescope called the Australian SKA Pathfinder, or ASCAP. That observes higher frequencies, so around a gigahertz, but still these same radio waves. Now, these are both located out in the Western Australian desert, which is where we're building our new telescopes on the road to the square kilometre array. You might have heard of that. It's a $1 billion project split between South Africa and Australia, where we're developing a telescope that will be able to detect the moment when the first stars formed in the universe. Now, the interesting thing is the telescope that we actually made our detection with is a bit of an older telescope, and that's called the Australia Telescope Compact Array. And I'll just turn the sound off there. So this is a telescope that's located in Narrabri, New South Wales, and I've been out here many times to observe. So our new telescopes, we operate completely remotely. Narrabri is also operated remotely now, but when I was training as a scientist, I would regularly go out here to observe with it. So basically, these are 6 dishes that are arranged on a railway line so that you can move them into different configurations, and they observe a range of frequencies from gigahertz to 100 gigahertz, basically. So you're looking at much higher frequencies. Now, this telescope is much more sensitive than those first 2 I showed you, but can only see small areas at a time. And so in this case, we were using multiple strategies. The other telescopes allow you to scan the sky more quickly, but once your object has been located, and in this case it was located by the optical telescope, you can zoom right in on it with a much more sensitive observation with these telescopes, the compact array. So, when we're building a radio telescope, it's a little bit like the issues of having an optical telescope where you want to get away from the city lights. So if you're building an optical telescope, you don't build it in Sydney because you wouldn't be able to see that much. You go out away from the light. Now, light isn't a problem for us in radio astronomy, but what is a problem is every single device you have like this. So every time your mobile phone communicates with the mobile phone tower, which it does even when you're not making a call, it regularly has little ping communications. Every time you turn off or on a microwave or a computer or drive a car or anything with any kind of electronic device in it, you're creating what we call radio frequency interference. So that is, you're creating radio waves at exactly the same type of frequencies that we're trying to detect from the distant universe. Except the difference is that the radio waves generated by your phone, if it's right next to my telescope, are so powerful in comparison to the faint radiation we see. Of course, that radiation was actually much more powerful originally, but so far away that by the time we detect it on Earth, it's a tiny, tiny faint signal. And a signal from your mobile phone will completely blast it out, and we won't be able to detect it. So when we build our new telescopes, we're building them in what's called radio quiet zones, where you can't bring devices like this that will destroy our observations. That does come with its challenges. So in fact, one of the interesting things about the MWA in particular is that it's very cheap and easy to build. This is a bunch of students building literally the telescope that we're using. It's almost just a kit you can get and put it together really easily. Having said that, I've never actually done it myself, but but I have connected it to the radio. Last week, for the first time, I used one of these antennas and listened to the radio. It was like a breakthrough in my understanding of physics lab. So it's really easy to build, but then deploying it and running it in the desert is a real challenge. You're far away from power, you're far away from your data storage. We have regular lightning strikes that wipe out bits of the telescope. Engineers have to go out on these special missions to fix the telescope in extreme desert heat, and mostly as astronomers stay back at our computers and do all of this analysis remotely. So the way that we do astronomy is completely changing. It's probably not how most people would imagine that astronomy is done. We're certainly not sitting there looking through a telescope most of the time, but what we are doing is downloading terabytes and terabytes of data and transferring it back to Sydney so that we can do our analysis. So that's radio astronomy. Australia is actually a world leader in radio astronomy. We have a great history. That's a whole different lecture, but basically started in the development of radar in World War II. It's a fascinating part of Australian history. But to go back to this story, so that we can finish the lecture, the story so far is this is a plot showing time after the gravitational wave event and all the different observations and detections at different wavelengths. So the time on this left part has been compressed here because it's in seconds, and then the time on the right part of the plot is in days, and the scale is logarithmic, so you have to sort of stretch it a little bit when you're looking at it. But we'd got gamma ray observations, we had optical observations, we had X-ray, we had infrared, we had UV, but we still didn't have radio. So our team had been working on this for a couple of weeks. We didn't really know. The theories predicted that we could detect radio emission within seconds or as far away as weeks, months, or years, or maybe never. So that's the thing about science. You're truly doing something in the unknown, doing this regular monitoring in collaboration with our US colleagues to try and make a radio detection. Why do we care about making a radio detection? Each one of these wavebands gives you unique information that you can't get in any other way. So what radio tells you is firstly the energy of the original explosion emitted in electromagnetic radiation, and it also tells you, because it's coming from a shock that's propagating into the medium around the stars, it's actually giving you a kind of forensic history of what the material around the stars were like before they exploded, because the shock is actually traveling out through that material. So you're getting that information that doesn't come from the other wavelengths. So that's why we were still keen to make a detection in radio. So finally, after 2 weeks, and this whole time, we have these GCNs, these circulars coming through, hundreds of them, as all these teams around the world reported their findings and their non-detections and so on. We got word from our colleagues in the US that they'd made a really tentative detection of radio emission. And so we asked for another day of observing on the Australia Telescope Compact Array the next day, and they gave us a whole day. And we also made a really tentative detection, and then we all spent several days debating whether we really had a detection or not. Now, what it looked like in the end was this, and for those of you that are not radio astronomers and who love David Malan's incredible images, I have to apologize that radio astronomy is normally a disappointment. So what you see in this image, just to explain it, and the lights again. Okay. So what you see in this image, in the center of the image, bright things means that means you're detecting some emission, and dark means that you're not. So in the center of the image is the supermassive black hole at the center of NGC 4993. So you're detecting the galaxy. Okay, that's what you see there. Now, between those two white crosshairs, you see, hopefully, a very, very tiny sort of reddish dot thing. Yeah, that is the radio emission from the neutron star merger. So, look, on the one hand, it is kind of disappointing. On the other hand, it might be the coolest thing that anyone on my team has ever observed with a radio telescope. And being part of the first few people in the world to ever see this tiny little red dot, everyone was so excited, and particularly after 2 weeks of flat-out work. And so it might be a little bit disappointing, but it's actually the first time this has ever been observed in human history, so it's pretty cool. The only problem is that I kind of lied. That's not what we saw 2 weeks after. What we actually saw was this mess. So this image, so what I showed you there, this is the published detection that got us a nice science paper. But this is what we saw on day 15. So on the left was the observations from our colleagues on the Very Large Array in the US, and on the right was our observations the next day. And so this is because at this point the object was quite weak and we didn't have very good signal to noise, so we couldn't detect the signal very clearly. You'll see what I mean by tentative. So, well, actually, the Americans were pretty confident. Oh, this is streaming. I shouldn't discuss. Okay, we were not so confident. But this is, again, the center. The big blob is the galaxy, the supermassive black hole at the center of the galaxy. And the little blob to the top left is what we thought was the new source appearing. And the next day, it was pretty marginal. This was not normally at the level of significance an astronomer would accept as being real, but it was a really good tantalizing hint that there was something there. The next day, our observations, again, on their own, we would have thought this does not seem real, but the same tantalizing hint in the same location as the previous day, we were starting to get excited, kind of at a really low level of excitement where we were hopeful but not convinced. So then over the next few days, we did more monitoring, and ultimately we got this detection, which you'll have to trust me, is actually quite convincing for a radio astronomer. It may not be if this is the first time you've ever seen a radio image. So I kind of explained what causes this, but just to recap, when we have our neutron star merger, the first thing that happens at the moment that those neutron stars form is the generation of gravitational waves that travel through space 130 million light years to get to us, and were detected by LIGO. After the gamma ray jets have come out, and after the cocoon of material has exploded into space, just after this bit of the animation finishes, a huge shock is generated, and that travels through the material around the star. That shock accelerates electrons and generates the radio waves that we then detected. So, putting together all of this, we end up with a really cool story. Now, this is something that happened in a period of just 1 month of scientific work with about 3,500 people. So this was intense science. There was laughter and there was tears. It was really intense. There was hundreds, thousands of emails. There's no astronomy follow-up campaign that's ever been done on this scale. So this is really big science. And there's a lot of collaboration and also fighting and stuff that goes on with that, but mainly collaboration to make this happen. And so what you see from the beginning is this nice schematic that LIGO has put together that explains every part of this and how each bit, each wavelength that we observed in gets put together to tell the full story, from your gravitational waves through to your gamma ray radiation, through to your optical kilonova, where we detect the gold and platinum, through to the radio remnant as this shock wave propagates through the interstellar medium. So that's the full picture. It's been super exciting to be part of this huge scientific effort and to have contributed a tiny little part to this big picture. These extreme events are basically our laboratories for understanding our universe. There's no other way that we can investigate this physics except by doing these observations. And putting it all together gives us a completely new window. So we're really excited about this new era of astronomy. And at that point, I'd like to stop and take some questions.